Welcome to Science Lab. The signs are happening because Jesus is coming. Every day, we are looking at some of the signs that are happening around us. In this episode, we are going to see about the strange things that are happening in the sky.
Astronomers have begun one of the most far-reaching efforts ever undertaken to study the universe. They are forging giant new lenses and mirrors while marshalling vast computational power. These new technologies are at the center of a historic quest to peer into the deepest recesses of time.
To find out how the universe set the stage for galaxies and worlds like us, in an era known as the Cosmic Dawn, what forces came together to form the very first generation of stars and galaxies, and over time, the vast architecture of matter and light we see in our telescopes.
Only a century ago, astronomers debated whether the universe is confined to a giant rotating disk of stars, dust and gas, the Milky Way, or whether a galaxy is one of many so-called island universes. We now know that a galaxy is part of a formation of three major galaxies, along with some 51 dwarf galaxies called the local group.
The local group is bound by gravity to a much larger formation, the Virgo cluster, with up to 2,000 galaxies. Beyond Virgo galaxy clusters are linked to superclusters in a pattern laid out by the first great cosmic mapping project, the Sloan Digital Sky Survey, beginning in year 2000. As the Sloan data shows, superclusters are connected to each other by streams of filaments of galaxies bounded by immense empty regions. To understand how the universe got this way, astronomers must identify its basic components of matter and energy. Back in 1930s, the astronomer Fritz Zwicky measured the rotation of spiral galaxies like Milky Way. He found that the gravity that binds the stars greater than what he expected based on the amount of matter that's visible. Zwicky called the unseen substance exerting this extra gravitational pull dark matter. You can see its influence on even larger scales. Without dark matter, the gravity of clusters like this is not enough to hold all the galaxies rotating around it. In this case, dark matter acts as a lens, magnifying and distorting the light of galaxies into a deep background and causing them to appear as blue arcs. Astronomers used the pattern of gravitational lensing to map the distribution of dark matter in the supercluster Abell 1689, shown here as blue haze. On a large scale, galaxy structures like these are a measure of how much dark matter there is. This computer model shows the role dark matter has played in shaping the contours of the universe. Not long after the Big Bang, gravity gave to amplify slight initial variations in the distribution of dark matter. Regions of the highest density attracted enough visible matter from galaxy clusters, even as astronomers struggled to define that dark matter is they discovered another mysterious and powerful influence in cosmic evolution.
In late 1990s, two groups of astronomers asked whether there's enough dark matter out there to one day slow or even halt the expansion of the universe. Using the Hubble Space Telescope along with the ground-based telescopes, the team set out to track the rate of cosmic expansion through the entire history of the universe.
They did this by searching deep space for a particular type of exploding star called A-type 1A supernova. It often begins with two stars in a closed orbit, one of which draws gas from its companion. When it gains enough mass, it undergoes a runaway nuclear reaction and explodes.
Because type 1A supernova are all thought to blow up in the same way, they have the same intrinsic brightness and makes them ideal for measuring cosmic distances. It's like looking at the car headlights approaching in a highway. The dimmer they appear, the farther away they are. The astronomers combined distance measurements with another marker, how far the light has shifted towards the red part of the light spectrum. The greater this red shift, the more the universe has expanded since the star exploded. Some explosions appeared dimmer than the teams expected based on the red shift. That meant the light had traveled farther than it should have given a constant rate of expansion. This finding led the two teams to conclude that in the deep past, the universe was slowing down, but to reach its current size, it must have then sped up. Scientists now believe the universe is dominated not by matter we see, nor by the mysterious gravitational presence, dark matter. It's something else, persuasive and powerful enough to cause space to accelerate outward. They call it dark energy. One leading idea is that it stems from particles that well up from the vacuum of space. As the universe expands, it generates more and more dark energy that has the effect over large distances of counter-reacting gravity and causing space to expand even faster. Spread over the vastness of the universe, it is the energy equivalent of only 5 hydrogen atoms per cubic meter. And yet, scientists find that dark energy accounts for 68% of the entire cosmic matter energy budget, with dark matter at 27% and ordinary visible matter less than 5%. The twin discoveries of dark matter and dark energy has thrown cosmology into turmoil and potentially into a new age of discovery. Astronomers have now launched a full-scale effort to pin down the forces and events that drove cosmic evolution going back to the earliest times. Already a fleet of space telescopes led by Hubble is scanning the distant universe for light sources across the electromagnetic spectrum. The long-awaited James Webb Space Telescope, slated for launch in 2018, represents the next generation of great space observatories. With a segmented primary mirror that is almost 3 times larger than that of Hubble, the James Webb will capture the trickle of photons from a time nearly 13 billion years ago when the universe lit up with stars and galaxies. The next generation of ground telescopes will radically extend gathering power. The European Extremely Large Telescope, now under construction of Chile's Atacama Desert, will have a 39-meter mirror that quadruples the light-gathering power of the largest telescopes today. While these telescopes extend our vision into the deep universe of American W-FIRST and European Euclid space telescopes will take in large regions of the sky at high resolution.
These new instruments, each slated for launch in the 2020s, will be used to survey the deep universe for Type 1a supernova and other markers of cosmic evolution. These space observatories will work in conjunction with an ambitious new effort to track the evolution of the cosmos in near real time.
The Large Synoptic Survey Telescope, or LSST, is being built in the mountains of Chile. It combines data gathering on an unprecedented scale with plans for dedicated fiber optic connections capable of delivering a flood of data to supercomputers of continents away.
From there, it will be processed and made available through advanced internet links to scientists around the world. At its heart, the LSST will be outfitted with the largest digital camera ever built. That includes the largest lens ever built, now undergoing final polish before assembly. With a field of view the size of 50 full moons, the telescope will observe just over half the sky visible from the Earth to the depth of about halfway back to the beginning of time. Astronomers expect the telescope to record a blizzard of transit events, from asteroids buzzing through the solar system to black holes flaring in distant galaxies and stars exploding out on the horizons of space and time. The telescope will revolutionize what scientists call time domain astronomy. To make sense of the deluge of data This project will make extensive use of supercomputer models designed to simulate periods in cosmic history. These powerful programs are based on theories of star and galaxy formation, the influence of dark matter and dark energy, and a host of other parameters. The scientists will use them to test theories about what drives cosmic evolution by comparing simulation results with data captured by the telescope. The LSST project will build upon previous large-scale cosmic surveys. The Sloan Digital Sky Survey has mapped galaxies up to one-third the distance to our visible horizon. Astronomers are now leaving beyond that with a project based on a summit across the canyon from LSST. It's called Dark Energy Survey.
So far, we were seeing the beginning of time. After seeing all these things, we definitely need a break. Don't go anywhere. We will continue after a short break. Welcome back to Science Lab. The signs are happening because Jesus is coming. Before the break, we were seeing the beginning of time. Let's continue in exploring the beginning of time. Telescopes captures the light of stars and galaxies across the electromagnetic spectrum from high-energy ultraviolet to low-energy infrared. These colors reveal important galaxy characteristics such as the rate of star birth, the amount of dust or gas within them, their distance from the Earth.
The camera sensor divides the field of view into 62 high-resolution detectors. Each one captures countless thousands of celestial objects, some bright and well-known, others too subtle to see with your eye.
Night after night, month after month, the exposures pile up across a survey area that covers 1/4 of the southern sky or 1/8 of the entire sky as seen from Earth. With data from the Dark Energy Survey combined with a much larger LSST survey, scientists will create a three-dimensional map of galaxies going back into the universe was half its current age. In recent years, advanced telescopes have shown that the universe is filled with galaxies in a wide variety of shapes and sizes, from giant spears of ancient dying stars to complex twisted shapes, often run through with rings of dust. The historic Hubble Deep Field took us back for the first time into the early stages of galaxy formation. It found that the blurry scarps of stars and gas visible at the dark margins of space primitive galaxies. Theory says they will one day merge into a large, mature galaxy. Using the ALMA telescope array, in Chile's astronomer caught a glimpse of galaxy evolution in its earliest stages. They focused the telescope on the southern constellation of Cetus, setting their sights on a seemingly empty region. Deep within it, about 3.5 billion light-years away from Earth, lies the galaxy cluster Abell 1744. It's known as Pandora's cluster for the tangle of shapes created when at least 4 smaller galaxy clusters were merged together. To one side, astronomers found a faint, ghostly shape that had been magnified by dark matter within the cluster. It is a pocket of stars far beyond and much older than the galaxy cluster. The stars were being born when the universe was just 600 million years old. This animation recreates the ancient star cluster surrounded by gas and punctuated with supernovae. Over time, most star clusters like this would have merged with the galaxy. As it turns out, a small number have managed to stay intact over the billion of years since they were born. Astronomers have long known that the Milky Way galaxy is enveloped in a diffuse halo of stars, including some 160 large star clusters. M15 is one of the densest known. Gravitational interactions among its stars have caused them to pack in tightly. So-called globular clusters like this are like pottery shards found by archaeologists at the sites of ancient villages. One called Tarzan 5 has even managed to survive a fall into our Milky Way. It contains a population of relatively metal-poor stars that would have been born 12 billion years ago. There should be many more clusters like this in a wide variety of sizes that have simply not had time to enter the disk. Where are they today?
When the first round of data from the Dark Energy Survey was released, scientists began combining it for light that could be resolved as stars. They saw what they were looking for: tiny remnants of the Milky Way's birth star clusters, almost entirely devoid of metal content. These dwarf galaxies turned out to be a dark matter rich with about 10 times the ratio of dark to visible matter as seen in the galaxy as a whole.
This realization is central to cosmology's quest to link the early stages and growth of galaxies to cosmic evolution on the larger scales. That quest points to the ingredients of matter and energy that produced the very first stars at the cosmic dawn.
In fact, astronomers have found a telltale pattern in light emitted when the universe was just 300,000 years old, the so-called cosmic microwave background. In this image from the European Planck satellite, the colors indicate hot and cold patches produced by tiny variations in the energy of the Big Bang. To trace the evolution of this imprint, scientists are using a supercomputer model to recreate the eruption of stars and galaxies in a cosmic dawn. It begins in the darkness of the early universe, barely 6 million years after the Big Bang. Gravity draws dark matter into diffuse halos. With them, hydrogen gas forms clouds that become more and more dense over time. As gravity compresses the clouds, they begin to heat up, then finally ignite to form the first generation of stars. The stars are giants much larger than any today. One blows up in a powerful supernova. The model shows an environment transformed by the explosion of supernova litters its surroundings with heavy elements created in nuclear fusion: carbon, silicon, iron, and more. These so-called metals cause surrounding clouds of hydrogen to cool that allows them to collapse. Turbulence breaks them into smaller pockets. A cluster of small second-generation stars now begins to form. Here, a wider view of the scene almost 400 million years later. From data generated by the simulation, scientists are working to isolate the dynamics of galaxy evolution. Stars are being born where filaments of gas, shown in blue, come together. Ultraviolet light from these stars begin to strip electrons from hydrogen atoms in a process called ionization that causes surrounding regions to glow with visible light. The ionized gas appears as bubbles. They are associated with pockets of elevated temperatures, shown in red, as well as high concentrations of metals spread by supernovae, shown in green. The simulation reveals a dynamic that shaped the course of cosmic history. Heating from ionization tends to push the gas out that suppresses the rate of star birth. Metals, on the other hand, allow pockets of gas to cool and fall inward that increases the rate of star birth. So instead of star forming and collapsing immediately in two galaxies, the universe becomes a wide mix of hot and cold regions. Large and small star clusters and pockets of gas amid clouds of dust rich in metals. The small dwarf galaxies that astronomers have spotted hovering above the Milky Way are relics of this early period and of the galaxy's early years. The supercomputer model gives us a view of cosmic evolution advancing to an age of about 1 billion years. The scene is dominated by the star birth and by star clusters merging together into large formations. The universe continues to put the brakes on galaxy growth, while the star birth spreads heat, stifling the flow of gas into galaxies' metals from stars and supernovae, having a cooling effect that enables this flow. Many of these early generation galaxies join in a larger aggregations. Take the Spiderweb galaxy, 10.6 billion years light away, and close examination shows that it sits in the middle of clusters of galaxy fragments. This animated reconstruction shows the chaotic scene. Hundreds of small galaxies and patches of stars are interacting while drying in a matter from surrounding region. Starting in the early years of the cosmic dawn, the simulation shows a slice of universe in a region 350 million years across. The gravity of a dark matter gradually concentrated visible matter into galaxy clusters. At the center of large galaxies, black holes grew to supermassive proportions. As matter flowed in, they generated immense expanding bubbles of gas. These bubbles pushed beyond their galaxies, spreading waves of hot gas. The heating from these bubbles would slow the flow of gas into the clusters that allowed smaller galaxies like ours to form on the margins. At the same time, black hole winds seeded the wider universe with dust and metals generated by supernova.
Once upon a time, people thought that Earth is the center of the universe and everything, including the sun, moon, and stars, evolve around it. Later, they found the truth about the solar system and beyond. In these last days, every secret about the Earth, the universe, is getting wide open. Do you know why the knowledge is exploding? Daniel 12:4 says, "Many shall run to and fro, and knowledge shall increase."
All these show that what is mentioned in the Bible that are going to take place in the end times are taking place in our lifetime. We are living in the last days. Lord Jesus Christ is coming again very soon. Thank you for watching this episode. Don't forget to tune to the Science Lab next time.
Send us photos, videos, news, and YouTube links which are worth sharing. And also send us your feedbacks to our email address sciencelab@angeltv.org. If you have missed any of the episodes, don't worry. You can watch it again and again in our Science Lab YouTube page. But don't forget to like, share, and comment on the video.
Ask your friends and relatives to watch the Science Lab so that they will know that we are living in the last days. Remember, signs are happening because Jesus is coming.
Maranatha.